Hello and welcome back to the course on machine learning. Today we're going to cover off some additional comments about the naive Bayes classifier. Alright, so let's have a look. Today we're going to talk about three things. Number one is the question, why is it called naive? Number two is the P of X and how we can potentially drop it sometimes. I'll show you a quick shortcut. And number three is what happens when there's more than two features involved in your dataset. Alright, so let's get started. Question, why is this algorithm called the naive Bayes algorithm? Well, the answer is pretty simple. The answer is because the Bayes theorem requires some independence assumptions, and the Bayes theorem is the foundation of the naive Bayes machine learning algorithm, and therefore the naive Bayes machine learning algorithm also relies on these assumptions, which are oftentimes not correct. And therefore, it's kind of naive to assume that they're going to be correct. That's the reason why it's called. Let's go back to our example and see what that means. So here we've got age and salary, right? And based on those, we're using the naive Bayes algorithm to classify our data points into people who drive to work or people who walk to work. Well, the Bayes theorem, the way we apply it, actually requires that age and salary have to be independent. Well, the variables that we're working with, in this case, age and salary, have to be independent. And that is like a fundamental assumption of the Bayes theorem, and then you can only apply it, and then you can get those probabilities and so on. But in our case, if you just think about it fundamentally, it is probably not the case, right? Probably there is some sort of correlation between age and salary, because as a person gets older, their experience grows, their number of years that they've spent in the workforce grows, and therefore their salary grows. So it's natural for the salary to grow with age. It might not be a super strong correlation, it's not for everybody, but overall there is some sort of correlation. So they're not absolutely independent variables, and moreover, you can even see that from the chart. You can, just by looking at our chart, see that there's some sort of correlation between the two variables. And therefore, given that they are not independent, you can't really apply the Bayes theorem, and therefore you can't apply the Bayes algorithm to machine learning. And that's why it's called naive Bayes algorithm, because oftentimes it's applied even though the variables or the features are not independent or not completely independent. And it's still applied and it still gives good results. And that's why it's called naive, because it's a naive assumption. All right, number two, P of X. So let's have a look at what we performed. So kind of like rewind and analyze what we did in our steps in the previous tutorial. So in step 2, what we did is we took P of X. So when we were calculating P of X, we drew a circle around our new data point. We removed the data point just so it's not in the way. And then we shaded the area. And so what is P of X? Well, P of X is the likelihood that a randomly selected point from this data set will exhibit the features similar to the data point that we're about to add. And as we agreed, anything in that circle is deemed to be similar to our data point. Another way to think about it is, what happens if I throw in a random variable or random data point into this data set right now? What is the likelihood that it will fall into the circle? What is the likelihood that it will exhibit features similar to the features of the point that I'm about to add into the data set? So basically it falls into that circle. And so P of X is the number of similar observations, or similar observations means observations similar to the point that we're about to add, divided by the total number of observations, which is 30 in our case. So it's 4. We can see that there's 4 points in this circle right now, divided by 30. And the interesting thing here is that this result is the same both times. So this is in step 2. In step 1, where we were calculating for the people who walk to work, so the probability for people who walk to work, it was the same. So basically P of X doesn't change whether you're calculating it in step 1, where we were calculating the probability that the person with these features is a person who walks to work, or if you're calculating in the step 2 scenario, where you're calculating if that person with these features is a person who drives to work. And therefore it's the same both times. So what does that mean? Well, let's have a look at the formulas. So you can see that the formula in step 1, it was P of the probability of a person who exhibits features X, that he or she walks to work. And that was the formula, and you can see P of X is at the bottom. And for step 2, it was a probability of a person who exhibits features X being a person who drives to work. And as you can see, P of X is at the bottom here. So what did we do in step 3? right? So let's move on to step 3 from here. Step 3, we compared the two. So now if we take these two formulas, these right sides of the formulas, and put them into the comparison like that, you will see that at the bottom, the denominator is the same. Now that we know that the denominator is not 0 and it's actually greater than 0, probability is never less than 0, and we know it's not 0, so we can just get rid of it, right? We can multiply both sides by p of x, and therefore the sign won't change, and also we'll get rid of the denominator, and that way we won't actually have to perform that calculation. So that's one less calculation to perform. So you can just compare the top parts of these calculations. And so that is what is done a lot of the time. So if you've done other courses on machine learning, or if you've read some maybe articles on machine learning, you will find that this is oftentimes the case. And also sometimes it is not mentioned that this is happening. So sometimes it's assumed that, or it can be assumed that you know what's going on. So just be careful of that, look out for that. And it's a valid approach, as we discussed. It's totally valid to do it that way, but that is only if you're comparing the two, right? If you're only comparing the two, then you can do that. If you actually want to calculate the value, so we said 75%, 25%, if you want to calculate the value, you can't do that because it'll be too different to reality. It's because you're supposed to divide by a certain value. It's not the actual value. And moreover, if you want to, like, comparing is okay, but calculating the actual value and maybe performing some operations, or you calculate the value from this, you want to compare the value from this scenario to a value from another problem, right? Like a value from a different kind of a scenario where p of x will be different, right? Not from this particular example that you're working with. You want to compare the probability of the person being a person who walks to work in this example to the probability of that person being a person who walks to work from a different example, right? Where p of x will be different. If you want to compare across like that, that will also not work because your p of x is different. So be careful of that. It's always the safer way is always just to perform the full calculation. But if you're doing it often, or if you just want to save some time, or if you just maybe reading other literature, then it's also good to know about this approach where the denominator can be dropped when just comparing between the two. All right, so that was another point, or like kind of a hint there, or maybe a shortcut. And so the last point for today, what happens when we have more than 2 classes? So as you remember, in this scenario, we only had 2 classes, the red and the green, or the people who walk to work and the people who drive to work. What happens when we have more classes? How is the challenge different? Well, when we have only 2 classes, we compared, as you remember, we compared the probability that a person who exhibits features X walks to work. So basically that new data point that we added, what is the probability that it's a person who walks to work versus what's the probability that that new data point is a person who drives to work. And it turned out that we were comparing 75% versus 25%, and 75% was greater than 25%, and therefore probability of that person being a person who walks to work was greater than that person being a person who drives to work, and therefore we decided to classify them as a person who walks to work. And it's very straightforward, and moreover you'll find that every time when you just have 2 classes, it'll always add up to 1. So we didn't even have to calculate the second one. We could have just stopped at this one, because if this is 75%, this one is automatically 25%. It's always going to be like that if you have 2 classes. The way it changes if you have 3 classes it gets more interesting, right? So you've calculated 1, and then there's still 2 more left. So if you're working with just 2 classes, as soon as you calculate 1, you're done. You can decide right away. If it's greater than 50%, then you assign that class. If it's less than 50%, you assign another class. If it's equal to 50%, then you've got like a tie. Whereas if you have 2 or 3 or more classes, then just calculating the 1 won't be enough, because then you have 2 other ones and you would still have to calculate at least another one. So it just means that it's more of an interesting selection problem when you have more classes. That's pretty much the main thing that changes when you have more classes. And there we go. That's all for today. I hope you enjoyed these extra tips on the naive Bayes classifier, and I look forward to seeing you next time. Until then, enjoy machine learning.